everyone is settled down, and I'd like to welcome all of you to another lunch seminar of ICEE, which is Initiative on Clean Energy Environment, group of multidisciplinary researchers set up in Hong Kong 3 years ago. Today we are very pleased to have Professor K P Cheung, our professor in the Department of Architecture, giving a seminar on nuclear power plant safety. As all of us know about the recent disaster, unfortunate event in Fukushima, we already have one workshop and seminar a few weeks ago on this right here, which I was unfortunately absent in. I will make up for that here today. Professor Cheung doesn't need a lot of introduction. Some of you don't have his biography here. I will read a few important features. He is one of the special and unique professor with a broad background. Architecture and engineering sometimes don't like each other because one is too idealistic, artistic, the other is too practical. And Professor Cheung happened to bridge across two disciplines with experience and professional recognition in mechanical engineering and fire safety engineering. And now he's doing architectural work. And he has been a strong advocate of green facilities and was proposing to the Hong Kong SIR on the future 100 years of Hong Kong, how to integrate different facilities in a green manner. You can read about him quite a bit on various internet resources, including YouTube. I should have a slight small warning, not only about switching off your mobile devices, but also you may be filmed and appearing on YouTube, so which may not be a bad thing. So we just behave the normal way. Now, this particular talk is about Professor Cheung's proposal a long time ago, in 1991, about how to cool power plants better and a special design to avoid unfortunate events like the recent Fukushima. And at the same time, we have also an external guest, Dr. Fung, who just arrived. Will also help in the presentation discussion. So let's welcome Professor Cheung.
Thank you. Right. Now I shall use a PowerPoint slide. When it looks, the title look differently. Content in fact is the same. Because I try to put this to hit the audience search later on if I put it on the web. Okay. Now we have Dr. Fung to have the second part of the presentation, and here first part will be on the mobile pumps and liquid chilling units to cool Fukushima, another nuclear power plant in the world. The purpose is not to discharge radiation contaminated water into the sea, right? So let's look at what's the problems we have. Now, we have quite a lot of all these records of what's happening. I don't think I need to show you more than this. And in a normal way, you have cooling water coming out of the power plant intake from the sea, okay? So you notice this part. So second part, later on, when we move on a bit, you don't see the water there. You don't see the water here, right? So on this slide, you see water coming out, okay? That is from the plant, okay? Now you don't have it because that the accident occurred. So basically all the pumps and the system stopped, all right? So but that was, the buildings were intact before the explosion. And again, this is somewhere before the explosion, all right? And you have notes, this is number 1, 2, 3, 4, and this is 5, 6. Accordingly, you see here, this one is coming a bit closer to the seashore, 2, 3, 4, and then 5, 6 over the other side. So you see this one, right? This 1, 2, 3, 4, 5, 6. 6 reactor units, okay? So number 3 is there. So 1, 2, 3 is there, the first one to explode, right? So I don't need to go through this because we know what's happening. If you want to update, we have all the websites. Now if you click here, it is something really, you see how it's explained with all these happenings, all right? So you see that all these catastrophic consequences of that. Now, going to nuclear power plants, if you really want to study it, a lot of knowledge to go through. But basically, if the plant is stopped not to react to give you power, there is still something you cannot get away, which is the residue heat. Okay. Now this website, if you go there, it's giving you update of every day what's happening in Fukushima. And then here you see the decaying heat. It goes on more or less the same at that value, all right, continuously for several months to come. So this is the decay heat of the reactor. Now generally, as you look at this, for number 1 of the first reactor, the second and third reactors, okay, are of different value. Now it's about 5 to 10 megawatt decay heat, okay. So remember this figure. Now this is a boiling water reactor, and the spent fuel rods are put there, and it should be here too, okay. And then the system goes like this. If you go there, you have more explanation of this. And then this is a cooler, okay, for the going through this. Here is a residue heat removal heat exchanger, okay, and that goes with the reactor core. But during the tsunami disaster, these pumps basically did not work, okay. And also, if this is a turbine, say boiling water is that the reactor surface, okay, is in contact with water that is going through. So therefore, the water is boiled, and then steam comes out, and then going through the turbine system to move the machine to give you power, electricity. Okay. Now, if you look at this, this is where the reactor turbine. Okay. This is the mineralizer of the condensed water, and this is power plant system. But here is emergency water supply system going through this pumps to cool the reactor core. Okay. Now you have more descriptions here and there under different sources. Okay. Now my comment is that if you go to the TEPCO or the Tokyo Electric proposals, it will take a few months to build new coolers. Okay, it's what they are still saying, right? And then they're saying, okay, they'll do some cooling system to be put in, but it takes several months to work out. Okay, the French people have got experience with that. Now we have 3 days ago, we had problems with more radiation contaminated water flowing to the sea because of heavy rain of typhoon and because of breakage of the pipe. Okay. Now, it was 20 years ago that I wrote a paper. In those days, it was before the date of Daya Bay was built. Okay, 1991. Daya Bay power plant was built and operated in 1994. Okay, so in those days I said, hey, could we do something? If the power plant cannot do all this cooling system, what else can we do, right? So I said, hey, come up with a emergency heat removal system we can take the mobile pumps and liquid chillers, chilling units from the civil sector. Okay, so then we came up with that. Now everyone in those days, based on the PWR, which is called the pressurized water reactor documents that you can obtain from U.S. Nuclear Regulatory Commission, okay, NUREC, for information, right? Now, this piece of news was yesterday there, and then on the video clip you will see what's going on, okay? So I will put this on the web to make you to see the video, okay? But you know, I don't, because the web is not as quick, so I just leave it at the moment. It means that IAEA, International Atomic Energy Agency, sent people to look at the interior part of Fukushima nuclear power plants first time after the accident happened on 11th of March. Okay, so the Japanese people tend to hold lots of things back until at a time they feel they should let people to go in to see certain parts of the plant. So there's a lot of things that they clear off already. You don't know what's happening, in fact, right? So now they admit they have core meltdowns in 3 numbers of reactors, and it's going to be serious, okay? Now, the news of today, okay? The news of today, 31st of May, is saying that there is a Japanese organization looking at nuclear waste, and they're saying that the situation surrounding Fukushima would be as bad as the Chernobyl accident in 1976, okay? But that's what they are saying. I just took it from the news, right? So what can we do? We have something from the mobile side of tools. Now, let me tell you a bit more about this. Now, we have this type of equipment. Trend, it's a big company in USA. It's got subsidiary companies in other parts of the world to make lots of air conditioning equipment, all right? So this is what we call an air-cooled chiller, right? For those who study mechanical engineering, you work in air conditioning industry, you know what that is, okay? So this is a set of cooling coils, pump, refrigerant pumps, or motors are there, and all these, set up a closed loop system for cooling. What they need is, you have to put in a pipe to give the warm water, and then another pipe to get cold water out from here or there, okay? Now, 500 tons does not mean this is the weight of the equipment. It's an old name. It's about 1,650 kilowatt energy cooling capacity, okay? Now, remember, we talk about 10 megawatt. Now we have 1.65 megawatt, okay? 10 megawatt the gain heat from the nuclear reactor, okay? So this is about 6 times, okay, of that. So let's work out something later on. Now here you have a mobile diesel engine pump, okay? This is a diesel generator. This is a pump. So water is pumping and out from here, okay? You have this available easily, you can get it. And here is a mobile diesel generator. It's very easy. You get it across our street. You have all these, you know, working in the construction site. All these are common, right? You can get lots of this. So what we are lacking is that, can we have a mobile water chilling system to work together, okay? And then the pipes, do we have pipes and valves to connect these systems? Do we have pumps? Okay, we can do this and take it to the site, okay? We will take this to the site, okay, with the generator, power generator, to have to power this liquid chilling system, and then to pump water, and then here, this is the damaged Fukushima. Now, all this with the pipes connecting, that was the picture with the engine pumping water into the interior. So let us see, we have pipes, we have the pipes connecting, and all this quickly, it can be done within 7 days, okay? You take the equipment there, and then set it up. 1 system, it will work 7 days. 2 systems, 7.5 days. 4 systems, 10 days, okay? All this equipment can come I think in Japan, you would have this. It's a big industrialized country. You would have this type of mobile chillers to be rented out. In fact, in USA, it's very common. Okay, you need cooling for certain months, right? So here we said, hey, with a mobile water chiller, with a mobile pump, with a mobile diesel generator to give power to the machines, and this can be hooked up. Okay, take water, warm water from the nuclear power plant. The pipe connected to the pump inlet. The pump will push the water, goes through this chilling equipment, and the cold water will go back to the nuclear power plant. So this will form a closed loop. All right. Okay. Now remember, we talked about 1.6 megawatt cooling capacity, and then we can work out, okay, 6 sets of 1.65 megawatt. Okay, that will be about 10 megawatt. You look at this. So 20, 0, 20, 40, the decaying heat about, say, roughly 10 megawatt. So if you say we want to work with one reactor, we'll need 6 sets of this. So 3 reactors and then multiply by 3. All right. So that is not difficult. Okay. So first of all, if we can go there, we can help them, but we cannot go there. Okay. Japanese people will not allow you to go there. All right. And then the better that you don't go there, tell them what can be done. Let them think about it. Now, in the world, we have about 10% of nuclear power plants in the world in earthquake areas, sensitive areas. So about 50 plants. Okay. You got with 500 nuclear power plants, 10% in the nuclear active, in the earthquake active areas. So this is for the priority, okay, to provide this type of systems to back up the cooling, to make sure the containment building is not damaged. Once the containment building is damaged, oh, that's going to be lots of trouble, right? So therefore, there are another 400 numbers or more than that, okay, in other areas less earthquake sensitive. So Daya Bay is not an earthquake-free area. You still have earthquake in Daya Bay, but it is not as sensitive as it is in Fukushima. All right. So in Daya Bay, the design for earthquake was to the level, the scale of 4 in the Richter scale. Right. In other parts, it can be degree of 5 or 5.6 and so on. Okay. But you never know. An earthquake can come greater than the scale you design, all right? And there can be accidents happening larger than what you can face. Now, in Daya Bay, the design limit is that you break a piece of pipe of 6 inch, okay, or 150 mm. That is the limit of the design. But if this pipe is not that small, you break a larger pipe greater than 6 inch, 150 mm, so the cooling system say, we cannot deal with the job, okay? And an earthquake or power failure due to sudden lightning whatsoever, you can not imagine. Sometimes the terrorists can do some bad job on it, all right? So then you have a big trouble, all right? So what we are saying is, we don't know what's happening. So the design guideline there is not safe enough in terms of fire safety approach. As KY mentioned, I was trained as a professional fire safety engineer. We never trust the building on the equipment that is inside the building. We always say, if everything in the building is going to fail, what we can do. And we are as a team going to the site to help to deal with the situation. So therefore, the fire safety approach led me to put forward such a system. 20 years ago, lots of people laugh at it, all right? But we got to really serious about this, okay? Now, that is, okay, we try to make, we try to contain the building, okay? In case of damage occur in the nuclear reactor containment building, okay? So we don't want this to happen. But if that would happen, what can we do, all right? So this is very unlikely if we have a mobile backup closed loop cooling systems, okay? So now, I'm going to show more about this, okay? Now, it might be good if we it depends. If KY would like to have a stop and discuss about the cooling system first, because going through this, there are other things that looks a bit diversified, okay? And this will go to other systems that is related to cooling of the nuclear power plant and also protection of buildings and so on. Or perhaps it looks better for me to continue that, because if you come to here, you will see a few things. It's related to the nuclear power plant. Now, people say, hey, if the power plant is going wrong, reactor is going wrong, nuclear reactor, so what can we do? First of all, we have to stop the nuclear reaction, all right? So there are control rods that will go in and out. But suppose the control rods did not move. Now that was the case in Fukushima, all right? So the next action that people can do is to inject liquid that will stop or inhibit nuclear reaction. Now commonly people use borate solutions, all right? And here you will see a video, it depends on time, that in TV you saw that the Japanese military helicopters came, right? And a huge amount of water that you could see there from the sky. But I tell you, that is not useful. I tell you why. It's like pouring a heavy amount of water that came like a mass of water. So if I stood there, all right, I would be knocked out because the force is so huge. All right. If the rod stays there, and then if a huge amount of water came, and you will break the rod, and the rod could simply jump out of the pool. It's not an interesting job because it's a heavy amount of water that is simply thrown onto the side. But mind you, if you look at the video, that helicopter simply came like that. So 90%, 95% of water did not hit the target. But that was also the problem. Okay? So by doing this, we are saying, hey, can we do aerial dispersion of radiation suppression liquid, such as borate solution? Can we do cooling water onto spent-fuel rods or other parts? Okay, that was with the nuclear reactor. And then, can we do something on personal protection enhancement? Or can we do something on building protection against infiltration of nuclear dust? Okay. Now, on the last two parts of personal protection and also protection of buildings, I had joint research with Dr. Fung and other people for several years on this, and that will show something later on our tools that we developed. Now, that again came with a patent that I had with the support of HKU. I guess the patent is assigned to the ownership of HKU, but then the name of the inventor is still there. Okay. Now that was 5 years ago that I did a patent on this. Okay. The patent has several versions of arrangements of the helicopter and dispersion units. The concept is we can have an arrangement of 10-ton capacity steel cable. All right. So you can hold here about 4 tons of water. Okay. So the cable can be 200 meters long. So why should we have a cable of 200 meters long? When you look at the video of the Japanese helicopters, it's never as 200 meters long. It's like 30 meters or 40 meters from the nuclear reactor, right? If you get 200 meters, all the helicopter pilot will give you extra credit. It's because if you get as 200 meters above ground, if the engines there did not work, that is a technique called auto-gyration. Okay, you can use the technique. First of all, you can push a button. Sorry, you can push a button there. Okay, and release this weight. So there's a hook on the top of there. You release the hook, so everything will go out to the sea. Okay, then you can use auto-gyration technique to land your helicopter on ground. Okay, save the life of the pilots. If that is about 150 meters 200 meter for heavy, for larger engines, we need 200. Okay. So first of all, the pilots will be on the safe zone. Second, the helicopter can stay longer above the target. It's because whatever heat you can get above it, it never is damaging to the pilots if that is 200 meter high. And in addition, you can have water coming down. Okay? So on the hot air concentration, it does not affect the engine, does not affect the helicopter, does not affect the pilots. Two things. Third thing, now because we have GIS, all the GIS control of helicopters, okay? Then all this can be controlled within 1 or 2 meter accuracy. You can allow 5 meter, okay? So you can say, I allow 10 meter or 15 meter of these water spray nozzles above the building 15 meter. So if you say the helicopter can go up and down in 1 or 2 meter or 2 or 3 meter allowance, you still have 10 meter more clearance. It's a very, very big safe clearance already. Okay? Then water that came out can go, if you say, hey, 100 square meter. 100 square meter is 10 by 10. If you position it up to where the target is, all right, you still have the pendulum effect. Okay? But doesn't matter. It's because all this calculation can tell you when pendulum comes this time, you release the valve, water will come out. It passes, you close the valve, water does not come out. All right. Now all this control nowadays is possible. In the old days, 20 years ago, that was not possible. All right. So all these techniques are much easier. Okay. It's considered not high tech compared with the U.S. helicopter fighters. Right. This is not high tech at all. It's easily achieved. So we can use very easily achieved technology to give amount of water to the right target is in a form of heavy raindrops. Remember, heavy raindrops in 5 mm per minute of water density. So what is 5 mm per minute? 5 mm per minute is that you build a bund here, okay, and close a wall, right? So rain comes down here, okay. So you measure what is the level is rising up. So every minute it will rise 5 mm. It's double the density of heavy rain. Heavy rain is about 2.5 mm per minute, right? It's super heavy rain. It's 2.5 mm per minute. We say, hey, we double super heavy rain. With super heavy rain, it will not knock you down. It won't knock out the spent fuel rod out of the pool, all right? So it's a safe and efficient discharge of, if you say you use borate solution, it's very expensive. You don't have too much, all right, borate solution. But if the target, if with very effective and accurate discharge of borate solution, now you can accept it. Because the way that you do dispersion is very accurate, okay? So this is a technology now I can recommend to the world to work on if they really want to target for nuclear power control, accident control with this. And yet, we have to target for it. There are lots of nuclear facilities in the world. Not only nuclear power plants, nuclear laboratories, lots of here and there. And then, watch out, the terrorist is going to do something, all right? So, all these safety measures nowadays will be different from the old days now, okay? Nuclear power plants only came more popular since 1960. It's about 50 years, okay? It was after the time when I was born, KY. I'm old enough to say that for everyone here. So that, the first nuclear power plant was built before, after I was born, all right? So all this is about, the nuclear power plants about 50 years old, all right? And then we have more to come, all right? And then the atomic bombs came, you know, in year 1945. But that now we need to have better understanding and use of mobile systems. Now we have stronger systems other than this. We have another helicopter holding water reservoir and then coming up with the tube supplying all this. Now that's another version, but I'm not going to spend time on this. It means that this can be a proposal going to IAEA, Atomic Energy Authority agency in the world, and also to Fukushima power plants, right? But okay, so we have this, and if you want to see, have what done on this existing video, it was there. I don't think I need to go through with that, unless you really want to look at that for discussion. Now, I now move to another side of the content. Now, this is not with water spraying, not with cooling of nuclear power. It's now with protection. So what you have seen here, that I've done, I worked together with Dr. K. Fung and his students and other professional members since the SARS period of 2003. We worked this for about 8 years already. Here you see a student was testing a protective clothing for a person. So you will notice that it's a totally enclosed type of approach. Okay, it is inflated. Now why is inflated? It's because the filter air, this is the filtering machine. The filter air went into this, okay, with the tube of this clothes. Okay, so therefore it's inflated. And then there's an outlet. I do not show you. I would not show the face of the person. So that is escaping the heat. It's escaping at the head. All right, it's an opening. But the opening can be provided with a HEPA filter. I will tell you what a HEPA filter is. HEPA filter. HEPA filter. Okay. So a HEPA filter, it can do the job. I think I better go a bit further on. To tell you a bit more about the HEPA filter first. Okay, I think I better. Okay, this one. Now this is the machine you just saw in the photo. Is another part of it. So you see this FARR is a big brand making absolute filter, which is HEPA filter that we are talking about. All right. So the flow is from this side, from this side to that side. Okay. So airflow. And then you have the supply, the cover put in, here will be connected to a tube with a control valve, closing, opening, the filter air, okay? So what is the HEPA filter in fact? Okay. The HEPA filter, the HEPA filter, okay, is defined, okay, by DOE, Department of Energy, okay? And Department of Environment, right? Energy, okay, USA. Standard adopted by most American industries, okay? So it will remove at least 99.97% of airborne particles of 0.3 micrometers in diameter. Now, basically, all these radioactive nuclear dust are bigger than this diameter, okay? If you talk about SARS virus, the biggest SARS virus is about 0.15 micrometer, okay, in diameter. The filters, airflow drop, and so on, right? Now, there are different classification, and you can filter the particles to 99.9995%. It's still there. You got class 17 that can do a bigger job, all right? So it means that these filters are very powerful filters. So why do we have these filters in the world? It was because the original HEPA filter was designed in the 1940s, was used in the Manhattan Project. Now we know this is on the atomic bombs, all right? That the bombs that fell onto Japan, okay, Manhattan Project. Now to prevent the spread of airborne contaminants, okay, a HEPA filter was developed by USA at the same time when they developed the atomic bombs, and later on also with the nuclear power plants. Okay, now the filter is capable of filtering out airborne contaminants of nuclear dust. Okay, before you have air discharging out of the containment building. Now that was the purpose. Now it's becoming more common. People use this for other facilities for controlling virus. Okay, we can filter virus. Okay, and we can also, sorry, we can filter virus, we can also filter nuclear dust, and I will show you with the protecting equipment first. Okay, here you see this is the tool that you saw in a bigger photo just then. The HEPA filter is there, the fan box is there. Okay, the tube is that went into the backside of this clothing, and we can demonstrate that this person is better protected than any person that you saw in the TV or in photos in Fukushima. Because if you look at all these photos, they've got all these, you know, woods and so on, whatsoever. They have these breathing apparatus and so on. It's never a totally enclosed suit like this. Then you say, hey, are you doing something too expensive? I say no. If you buy one of these filters, it's about $2,000 Hong Kong. So we bought this. We went to a shop there in Yaomate and do the stainless steel assembly work and so on. You know, we work with this ourselves. All right, we know the cost of it, cost effective. And this, another doctor, okay, he made this suit, and we test it, it's super. One good point is, if you have the filter and a mask, all right, so the nuclear dust came here and deposited here, okay. Then you go here and there, it's still depositing on this mask. So once the nuclear dust came here, deposited there, then you got all the radiation from this nuclear source to this part of your body, which is not good at all, right? So what we are doing is, the filter is there, okay? The filter is there, the tube can be 20 meters long, all right? It's like what you see at the back. I like that picture very much. I like that picture, all right? This is a cleaner, so a super picture, very well drawn. It means that the filter can be there, okay? The tube simply come 20 meters to you. That is filtering the radiated nuclear dust, okay? So let all this collection be there. And the radiation was strong over there, don't go there, right? So the tube gives you good air, then you can breathe here, right? So that's what I say, with our proposal, we can do much better radiation control for people, for protecting people, than what you can see in the TV, okay? In Fukushima, that's point number one. Secondly, we have worked on with a demountable, okay, also for virus control, for infectious diseases. It's the same for nuclear control. I want this interior to be very clean. I can filter the air, and then I will inject air into this room to protect you, okay, from an environment free of radiation contamination. Okay, it's not difficult. Now, when we do this, you have to know, okay, this is a small version of HEPA filter machine. Okay, but this is in the HKU dental clinic. It was in the SARS period, 2003. Okay, so that a present line there was there, you know, to perform how this worker can be protected from SARS, supposedly to come out from this person, not affecting her, okay, or affecting him. So this is a type of personal protection tool that you can think about, okay. So we don't need to do expensive stuff to work out good things, okay, because the interior part is pressurized with sufficient airflow, and then all filter out with a HEPA filter, free of virus, free of nuclear dust, okay, it's clean air. So there, the worker also put on a N95 mask, okay, double safety, okay. So therefore, that is a test. So this is something on a mobile type of HEPA filter type of concept, and then that shows the protection of a mask, a hood for the head. Now, when we all do all this, we should know we are going to measure, okay, these levels of pressure differences across the room and outside. Now, the accuracy of this type of optic micromanometer is capable to measure to 0.2 Pascal accuracy, which means that we can control our room with very energy efficient devices for pressurizing our room free of radiation contamination and free of viruses, if we want to do so. Okay? Now that is important. The type of pressure measuring devices now commonly used in the building industry cannot work to that accuracy. Okay? So we are holding technologies that can work well. This is Dr. Fung setting up a smoke generator to test the smoke flow inside the control room, isolation ensuite with HEPA filter technology, and that is the machine. Now what we have shown, in fact, is that we have shown a few things in my talk. First of all, we can have a mobile cooling system that go to the nuclear power plants. Secondly, we have aerial distribution systems, and all these are our, if not very innovative, definitely something not copying from other people. All right. So we have a technology from here, and we have experience doing with air containment control for buildings, pressurized demountable ensuite, personal protection devices for viruses which can be extended for use in nuclear power incidences. And furthermore, in fact, we have a wind measuring devices. Now, lots of people in the world, including lots of engineers, lots of professors, misunderstand about wind. Lots of them, okay? Wind is drawn, presented to you like this. This is never a true picture. Wind does not go like that. It's hypothetical. Wind, as you see, with the wind rolls, that is given to you either by this website. I copy lots of the observatory data there with the maps on wind roses like this. Okay, all these are average values. Okay, it's hypothetical average values. In fact, it will go like this. Okay, if the wind is as steady as that. But wind, as we measured it, now it's presented by Hong Kong Observatory as this for the wind speed over the different hours, and then all these are in fact average numbers of every 1 or 2 minutes. Okay, so you average out all these numbers, give you one number. Average out all these, give you another number. So over the whole day, it looks like this. But we never come like this. I tell you how that perform. Now here, the wind direction is also given like this. It's average out. Okay, 1 minute average or 2 minute average. Now when we do measurement with wind, so at least we should do something like this. Okay, this is ultrasonic anemometer measuring wind speed in a vector format, giving you the speed. All right, giving you the angles, horizontal, vertical, so you know it's a vector. Okay, and give you every count as in time dimensions, 0.1 second. You can set it 0.1 second, even 0.05 second per reading. All right, so it comes to you, and then you have to measure this in an unobstructed area. Measure the wind eddy currents going through here, and this part is the free stream. Okay. So what you do is, actually, wind speed, as you can measure this, every division is 100 seconds as you go here. Okay? So within 100 seconds, you got all these changes of wind speed, big and small, all right? Sometimes like this, and then all this moving. And angle, in terms of horizontal angle, you see 0, 90, 180, 270, 360, and all this means north. Okay, 90 degree east, south 180, west 270, 360 going back to north. So it means that on the horizontal angle, here is like every 100 second count, you have all this varying like this. Okay? Within a short time, wind will go here from this direction and then another second like this and going back, right? So, and also, the vertical angle, 0 means it's horizontal. Okay? Minus 90 means it comes up from bottom. 90 means it comes from the top. Okay, and all this can change. It's not only horizontal; it can change. All right. So you can imagine, in 100 seconds, the wind is changing on the vertical angle, horizontal angle, and the speed. Okay, and therefore I tell you, if we are doing the job, okay, if we are doing the job for controlling, okay, infiltration of nuclear dust in the buildings, the average values are not suitable at all. You have to have no instantaneous conditions, but instantaneous conditions are so varying. All these data always vary. So how can we do it? And then another point comes: how can we clean the building? And then we have to know where will all these airborne nuclear dust come. So if you look at the average perimeter of the building, not everywhere you have average condensate or deposit of nuclear dust. Certain area you have a current, air current comes with a stagnation part, you have loss of dust there. Like what you see in the street. Sometimes you see, hey, the leaves are coming like this, right? So and then the leaves stay there. So these are where you have more dust. Okay. So therefore there's a need, if we want to protect buildings, how can we clean the building in exterior? So how long will the nuclear dust stay to make harmful effect to people? Okay. So then, what type of nuclear radioactive substances that will come to us? Basically, iodine, generally, right, from the air, right. So then, what next do we do? Do we tape all these windows, tape with strong tapes, or do we use 嗰啲保鮮紙嘅咁講？嗰啲我唔識講英文。There are some transparent wrap, right? You wrap the food. The wrap, people use the wrap to do all the sealing of the windows sometimes. Okay. How do we seal the window? So if you're doing 100 in Hong Kong, around this district, we might have 80 buildings, 100 buildings. So in case of nuclear accidents, can we identify 20 buildings you can stay on better, and another group of buildings not that good, right? Because infiltration can be serious. Okay, when we stay there, what next do we do? Are we all drink water, go to the toilet and flush water whatsoever? How long do we stay here? All right. So we have to say, hey, will power be disrupted? If there's no power, better not to go to certain buildings you cannot walk up. All right. And then you have water limited in the building for you to drink. Okay. So better not to do all this shower, a few days, and save the water for drinking, because that will save your life. All these are not clear to people in Hong Kong, not clear to people in Japan, not clear to people everywhere, until the nuclear accidents come. And then we have all listen to the radio, TV, and trust the government. And the government people, they do not know too much about all these, what to do, all right? They do not know better than I do, I think, all right? So what next do we do, okay? So that can be some discussion later. Okay. So what next? So I think I leave it for discussion, and I have to acknowledge all your coming and with acknowledgement on ICAE for the support. Okay. Thank you.
KP has unlimited interesting ideas. So in order to explore his ideas, maybe the audience here can take an active role and tap his mind and raise some question.
Now,
the topic and also an issue, nuclear power.
Okay. I have to report some effort that Dr. Jacqueline Nam has put together, who coordinated a group of people. Dr. Fung and I also participated, and a few other people. And everyone here, in fact, will welcome that, because we move on with a joint research on nuclear safety, stakeholders, and policies, participation, and so on. But it will take some time to work for that to get on, So good ideas, everyone's opinions will be welcome. And we'll try to let people involved in it, all right? So the importance is nuclear safety can never be overlooked. Okay. Now, people want to get away with nuclear power plants. In Germany, they say, hey, by 2023, all nuclear power plants in Germany, they got 17 numbers now. 17. All this will be closed down. Okay. But Germany will suffer from economic development. They will not have power enough to support economic development if they really want to cut nuclear power off, unless they invest overseas, which means that they move their investment up, their energy consumption up from Germany and go elsewhere. Okay, you watch out. Okay, this is important. Okay, and there are other nuclear power plants being built in Pakistan, in other countries, in China, lots coming up. All right. What we can do is, my part is to try to give good possible ways to reduce damages, okay, have cooling, protection whatsoever, as I can do. And I hope everyone would also put some effort into it. Okay, yeah, free for discussion.
Now we should also sometime maybe enlist the idea of Dr. Fung.
Yeah, yeah.
Whose picture up here.
Yeah, right.
Please help yourself with some sandwich. Now, a common and popular question is a simple black and white question, yes or no, and pro or con. You studied this at great details since 20 years ago.
Yeah.
So, you taking the view nuclear is a necessary evil or something that can be avoided? Or, so can you answer in a simple way, yes or no?
Okay.
Or is it just about coffee and tea? Is it, that you can, just one of the choices that you can do without? So
okay. Let me put it like this. Okay. To answer these questions, there are two steps to look at it. Okay. First step is to respond to your question and list out all these calculation and numbers. Okay. Second step, the second side of it is that there are nuclear power plants exist in the world. So every plant has a chance to go wrong next day, big or small. Right? It's never 100% safe. Okay. So therefore, on the nuclear safety aspect, it's a need to move along that. Okay. So that's clear. And if people live in a normal way, that we use energy. And if you're looking at the population increase in the coming years, okay, if we calculate the way that we can put solar power to be useful and so on, and I do not see, if we look at statistically, okay, the matching of energy demand will be without nuclear, but can work if we really want to match that type of demand. As we look at industry, of course, by political actions we can cut away something next day. Now that is another way. But on statistical observation, I do not see the chance. But that's what I see. But personally, I would say I do not stop technology on nuclear, because the worry is that people do not take enough safety steps. Okay, so I take extra safety steps. Now that shows the responsibility, which means that if I do this, I'm going to live next to the power plant. If they don't allow me to do the mobile system, I say, hey, I better get away. All right, because there's some possibilities and technology is there for people to work with safety. We have the HEPA filters and so on, but people simply ignore them. So if that is not safe enough, then we would object the use of it. Which means that the safety measures have to be very stringent, vigilant. Okay. Today I see all this, I will fail all these safety features in the nuclear power plant to my standard. Open up some discussion.
Statement seems to be
I should support
unavoidable
nuclear
evil
safety.
that may be necessary at least for the next X number of years.
At least.
The practical response is to minimize the impact on us and improve safety.
Yeah.
Seems to be the
So,
consensus.
thanks, Dr. Cheung, for a very interesting presentation. I think it's particularly attractive to me because the issue is that beyond to what extent Hong Kong or Guangdong need nuclear, the inevitable issue that we have to deal with is that to enhance and strengthen the safety issue of the existing dynamic. So, are you aware that in IAEA they are interested in exploring to step up their contingency or alternative way for nuclear safety issues, like are they welcoming ideas? And then are there any process or mechanisms going on that they are looking into this issue at this moment?
Now.
Yeah, and then I think the safety issue is that how safe is safe enough. So if they adopt your ideas, and then I believe there should be some continuing process that you have to revisit the issue regularly. So that's what question is should be that reviewing the safety issues, how safe is safe enough.
Yeah, it's always the point. How safe is the type of level of safety. It would involve what are the equipment and manpower to be put in, to deal with safety. Now, if you look at all this equipment that I mentioned, in fact, this can come from the civil sector. And what you need to do is you have to have mobile racks, so the container or the trucks can take the mobile system to the site, all right? Now that would not involve too much money, okay, of the overall installation, okay? In fact, there could be better or more economic way of putting this together. But by doing this, of course, you have to have people trained to operate the system, the drill, exercise to make sure the systems will work in case of emergencies. It's like fire drill and so on, Now, in China, if you look at the amount of dollar invested into power and nuclear power and safety and the after effects, if an accident comes out, so the amount of money compared simply is negligible. Negligible. Okay, you don't need to count. In fact, so little money compared to with all these investment and consequences, and even you gain more. You gain more money or you gain more value by training people to face emergencies. Okay, so this I should say. Of course, there are other provisions to be made. For example, the connection point for the pipe. Okay, it has to be allowed there. Otherwise, it will take more time to work out emergencies. But as well, you can count. In China, you got several provinces here and there. Equipment from Guangdong can go to Hunan, can go to Beijing. It takes half day, 1 day, but that doesn't matter. If there's something serious, the first lot can come from nearby area, mobilizing. It's like army truck going here and there. All right. So that cost itself on this type of proposals a little, in fact. And second point about the diabetes safety issues and so on. I should say I do not know too well about it, how they react looking at Fukushima, all right? But there are lots of people more concerned with safety knocking on their doors already, okay? But what we need to do is to get ideas to be passed to these people. And then we need big groups, maybe lots of groups of concern in the society. Everyone take a proposal, hey, look at this YouTube video, whatsoever, knock on the door, hey, do it. And you have 100 people knocking on the door open a bit. 1,000 people knock on the door, it open half, right? And then more and more people will make the enhancement to come true.
I think in the last presentation on nuclear technologies, we also mentioned about how China will react to should there be a nuclear crisis happen, and what's the priority of the government. and it seems to us that China is certain to go for nuclear, and there's nothing that we, Hong Kong, can do should there be a crisis, because the last information would come to Hong Kong. So I think Taipei, the information in Taipei, if we follow the logic of the Chinese government, would be not very transparent, as we have agreed. And so what Hong Kong can do as the society would be very important to take precautionary measures before a crisis like that happens and affects Hong Kong.
Okay. Let me put it like this. Accidents, we can try not to have it happen. But accidents can happen. Okay? So when it happens, the most important thing is there should be no leakage of radiation contaminated water or air out of that containment building. But that's the target. Okay? Based on that, if we need to knock on the door and ask an open policy or protocol from Taipei management, if that happens, what would you do to make sure that an accident bigger than what you design, okay, will not make contamination to come up? Now that is the key issue we have to knock on the door and ask the government to say this from Hong Kong, okay? And the technology is there. It's nothing secret. It's nothing difficult, okay? Only people work on it, it will be safe. Much more safer, I should say. It's never 100% safe. No system is 100% reliable. You can make 99.999% filtering of the particles, but never 100%.
Just had a question.
Yes.
Yeah, because when we look at the Fukushima accident, it's sometimes we cannot blame it's a solely technical problem, because we from the press we can say that the Japanese government should have done something earlier, like pumping water into the reactor or such kind of things, should have done earlier than they did, right? So my question is, will there be more political issues rather than just technical or engineering solutions to solve such kind of potential hazards in the nuclear sector? This is the first one. The second thing is, every time when we look at the nuclear accidents, I think most of the people have learned from the issue in 1986. Hey, we won't repeat it again, because due to that kind of problems. Now when we look at Fukushima, we may think that there's something we have learned and we will not repeat it, and it won't happen like this again. But sometimes, I don't know, later there will be another issue that may be different from Fukushima or from other else that we have not ever been thinking about of the problem. That because your system, it seems that it's quite only target the cooling system. We don't know other the cooling system, other part of the nuclear, the reactor or other part that may also have problems that we may not have think about. Yeah.
Okay. Okay. Let me respond like this. Now, in the Fukushima case, there are two countries to be blamed: Japan and USA. It was in the 1950s, late 1950s, that the Fukushima power plant was designed and planned. All right, only with the approval of U.S. government could that be done, because Japan lost the war. And still today, you got soldiers and armies from USA stationed in Japan. They have no control of nuclear power, weapon whatsoever, right? Then the design went to two governments, Japanese government and US government, and it was approved by two governments. So these approval people had to be blamed, because it was in 1933, the tsunami in Tokyo Park came 28 meters tall with water. And Fukushima, they said, it's designed 5 meters tall water. It's totally unacceptable. As an engineer, I will not accept it. So those people who approved building these plants should should take responsibility. But most of them do not exist in the world today, right? And that was the case, okay? Secondly, there was lots of, we read from news that action was wrong here and there for Fukushima. So I don't think we need to explain about it. There could be other things behind. But if you look at the mobile systems that I'm proposing, it can work for Fukushima because the building did not explode in the first day. It exploded about 20 hours later. It's because the heat is still building up, no cooling, simply no cooling. It's like what you're going to see, right? It's simply there, heat is generated, heat is not taken out of the building. So my cooling system is so-called cooling system, but the water can go to whatever places you need in the building. But you have to plan for it to make the most efficient way, all right? Never. The chilling system can work directly with the nuclear reactor. It's because nuclear reactor, to make it stable, water never comes down below 20 or 30 degrees. There has to be high temperature, maybe 80, okay? That would make the reactor stable and comfortable. The reactor rods do not react that much at 80 degrees centigrade. It reacts more at 20 degrees centigrade. It's something that we don't understand. I mean, I don't understand too well. But that is the case that we look at the stable temperature of reactor rod. It's not at the normal room temperature. A chilling unit cannot take water from 80 degrees centigrade. It's too hot for the moving parts, too hot for the refrigerant going through another cycle. It has to come down at about 10, 20 degrees, 30 degrees, doesn't matter. But then there is a level in between. You got to make all these arrangements. So what I'm saying is, the containment building has to be there, right? And the cooling, it goes in and out. That is the system that can provide you closed loop cooling. You don't need to dump water into the sea. But the cooling system is got air. It's like what the air conditioner, window air conditioner can work. The air can take the heat out of the building into the atmosphere. Atmospheric air cool the equipment, putting hot air into the atmosphere. So therefore, the purpose of this is to give a closed loop. Whatever to be done inside the plant is with the workers. We cannot take their place. They know what is the best to be done, given that we can supply enough cooling capacity, which means that, okay, all the decaying heat add up to that amount of heat. But we say, hey, we can have all these cooling systems to take this amount of heat out. But how you go inside and out, mix that amount of water with that and pump it out, we can give you a pipe connection. But within the building, we are not qualified to work on it. So, I mean, the line is clear, all right? So the system there simply have to be understood in this way.
Okay, so
yep.
That seems to be a good time to conclude. We can still continue discussion, but we should thank Professor Cheung for his enthusiasm in delivering interesting lecture, and to thank him, we have the usual souvenir. Thank you again.
Okay, thank you.
And wait for Peter to take the picture.
And I should share this souvenir with the Dr. Fung. Yes, we wrap this for.
So you can take this and you can take the
right, good.
RAM, right? That's how you share.
Yeah. Thank you, K. Thank you. Thank you.